Hello and welcome back to C++ Real-Time Audio Programming with Bela. This is the second video of a two-part lecture series on the MIDI protocol. In the last lecture, we talked about handling MIDI note-on and note-off messages to make a basic synth. Today, we're going to extend our understanding of the MIDI protocol to encompass the pitch wheel, the modulation wheel, and the controllers that you'll find on many keyboards. Over the course of this lecture, you'll learn how to handle these MIDI messages, and we'll also learn a bit about low-frequency oscillators and Portamento, which we'll use to add extra forms of pitch control to our synth. By the end of this lecture, you'll make a relatively complete analog-style monophonic MIDI synth. It will respond to note-on and note-off messages, the pitch wheel, the modulation wheel, and it will allow various parameters to be adjusted by MIDI controls. The companion materials for this lecture are available on GitHub at the link at the bottom of the screen. As always, you'll need a Bela starter kit or a Bela mini starter kit to run these examples. We also assume that you have access to a MIDI keyboard to plug into the Bela board. If not, there are various forms of virtual keyboard software which you can download. This is discussed more in the previous lecture. Now, if you're just joining us and you're not already familiar with the MIDI protocol, I recommend starting with lecture 15, where we cover it in more detail. One of the things that we saw in the previous lecture is that the fundamental unit of MIDI is the message. Essentially, every kind of data from your controller to your synth is going to be sent as packets of 1 to 3 bytes of data. In the last lecture, we saw various different types of messages, including note-on, note-off, control change, pitch wheel, and so forth. And we saw how to interpret the data within these messages. We also looked at how MIDI was specifically implemented on Bela, which is based on the Linux ALSA drivers. The advantage of this approach was that it's widely compatible. Any MIDI device that will work on a Linux system will work on Bela, and every source of MIDI data should work equivalently in your program. The disadvantage we saw is that ALSA doesn't provide the hard real-time guarantees of the Bela audio task. This means that in principle, MIDI messages could be delayed when the system is loaded. In practice, our experience has been that there's very little latency to MIDI messages in most circumstances. For this lecture, there are two sources of MIDI data that you might use. One would be a physical MIDI controller plugged into the Bela board, probably by its USB host port. The other would be a virtual MIDI interface where MIDI messages are sent from the computer to Bela over the USB port. You can choose which one of these you use based on the string you pass in Bela's setup function, as we'll see in a moment. In the last lecture, we talked about how to find which devices are connected to your board. There are a few things we need to do to use MIDI in our Bela programs. First, we need to include the MIDI library. Second, we need to make a global variable of type MIDI. This is the object that will handle all of our MIDI communication. Third, we need to initialize that object inside of our setup function. We'll tell it which ports to use and other settings that we need to get started. Finally, in the version of the API that we saw last lecture, we'll get our MIDI messages inside of the render function. When the MIDI messages arrive to the Bela board, this library will collect the messages inside of a buffer, and then inside the render function we can find out what messages are in the buffer and process them one by one. As we gathered each message, we checked what type of message it was, and then we took the appropriate actions. Another approach to using Bela's MIDI library is to declare a callback function. This is a function that you write, and you tell the Bela MIDI library to call your function whenever a MIDI message arrives. To use this approach, we first need to declare a function. In this case, I've called it MIDI event. Then, inside of Bela's setup function, we need to call this method called setParserCallback. This tells the MIDI library where to find your function. Finally, inside the callback function itself, we are passed a single MIDI message that has come in. We can then check its type and take the appropriate actions depending on what kind of message it is. If you use this version of the Bela MIDI API, your MIDI event function will be called in a different thread than the audio thread. This matters for a couple reasons. First of all, it means that you can't directly generate any audio events from within your MIDI event function. We have to wait till the render function to do that. Second of all, it means that any data that needs to make its way from the MIDI event function to your render function is going to need to be passed there somehow. The simplest way of doing this is with global variables. Which version of the API you use is up to you. Last lecture we saw the version where all of the MIDI messages were handled inside of render, so this lecture we'll look at the version where there's a separate callback for your MIDI messages. Another consideration that we saw last time was to remember that MIDI messages were fundamentally asynchronous with the audio messages. They might come in at any time relative to the audio block, and there's no easy way to know exactly which audio frame the message was received at. The problem that we had with that was that it meant that we could potentially have a small amount of jitter in responding to the MIDI messages. On Bela, because the audio block size is very small, this is not going to be a very noticeable effect. But one thing that is more important is to remember that every MIDI message has a persistent effect. If we have a note on message that comes in, for example, we need to remember the fact that the note should remain on until a note off message comes in. This means that when we receive MIDI messages, we typically want to update the state of our program in some way, oftentimes using global variables or other persistent data structures. In a moment, we'll see why this is important for handling the pitch wheel message. In the last lecture, we looked at MIDI note numbers, and I'm not going to talk about these again in detail. However, I do want to revisit the formula that we use to go from MIDI note number to a frequency, because we'll need this again to work with the pitch wheel. Remember that the A above middle C was defined to be MIDI note 69, and that it also has a frequency of 440 Hz. On this basis, we were able to work out a formula to take us from any MIDI note number to a frequency. We did it as follows. First, given a note number n, we calculated the number of semitones above A440. That came out as n minus 69. Then we took the number of semitones and we converted it into a number of octaves above A440. That was n minus 69 divided by 12. Given that expression, we were able to use an exponential function to convert the note number to a frequency as follows. The output frequency is equal to 440 Hz times 2 to the power of n minus 69 divided by 12. This formula will work for any MIDI note number, and in fact it also works for fractional MIDI note numbers. Although the MIDI note on and note off messages only send integer note numbers, when we get into working with the pitch wheel, we'll find that it can be helpful to be able to work with fractions as well. Now let's look at the pitch wheel in more detail. The purpose of the pitch wheel message is to create a change in frequency relative to where that note would usually sound. Because this is a relative change and not an absolute value for pitch, this means that we need to know both the note number and the most recent value of the pitch wheel message in order to figure out the frequency of our oscillator. We saw before that MIDI messages come in sequentially, only one at a time. That means that we're always going to need to remember the note number when we receive a pitch wheel message, and vice versa. The format of the pitch wheel message we saw last time, it was notable because the pitch value was stored not in 7 bits, but in 14 bits split across 2 data bytes. Our first task is to reconstruct the 14-bit value from these 2 bytes. The most efficient way to do this, especially on embedded hardware, is to use the bit shift operator to shift the most significant bits left by 7. In effect, that means that we are multiplying the most significant 7 bits by 2 to the power of 7, or 128. After we've done that, we can add the low 7 bits and we get a 14-bit number. On any modern compiler, you can equivalently multiply the number by 128, and it should produce the same instructions as a bit shift left by 7. Once we have this 14-bit value, we need to convert it into a pitch bend measured in semitones. The range of any 14-bit unsigned value will be between 0 and 2 to the 14th minus 1, that is to say 0 to 16,383. The center value of the pitch wheel is exactly in between this, 8,192. That corresponds to no bend or 0 semitones. A value of 0 from the pitch wheel is going to correspond to a bend downward of 2 semitones, and a value of 16,383 will correspond to a bend upward of 2 semitones. The pitch wheel range is also adjustable using something called RPN control change messages in the MIDI spec. I'm not going to cover that here, but I'll put some information in the companion materials. Now let's ask ourselves, what function might we use to do a linear rescaling from the 14-bit value to the range -2 to 2? The answer, of course, is the map function, which we've seen many times before as a way of rescaling values. Once we have the semitone bend value, we can add it to the original MIDI note number. Then we can plug the sum of the MIDI note number and our bend value into the MIDI to frequency formula as follows. That will then give us a frequency in hertz which we can use to set our oscillator. There's another equivalent way of handling the pitch wheel. When we get a pitch wheel message, we can convert its pitch bend directly into a frequency ratio using the formula 2 to the n over 12, where n is the amount of bend in semitones. Then we can store that value, and later, when we need to set the frequency of our oscillator, we can multiply the frequency of the MIDI note, which we have previously calculated, by the frequency ratio that came in from our pitch bend. These two approaches are exactly the same except for the format of what kinds of numbers we store. In the first version, we stored the MIDI note number as an integer and the pitch bend in semitones, and then we calculated the frequency once using their sum. In the second version, we instead store the frequency of the note in hertz and the ratio of the frequency from the pitch wheel, and then we multiply them together when we set the frequency of our oscillator. In today's examples, we'll use the latter approach because it becomes more simple for reasons we'll see later on. This brings us to our first task. In the companion materials, you'll find a project called MIDI Pitch Wheel. This implements essentially where we got to at the end of Lecture 15, except that I've changed it to use the MIDI callback API rather than processing the MIDI messages inside of render. Therefore, all of the MIDI messages are handled inside of a function called MIDI event, which is called by the Bela system whenever a new MIDI message arrives. What you need to do in this task is add a new if statement to detect messages of type KMM pitch bend. These are the pitch wheel messages. When you find a message of this type, you'll need to extract its 2 data bytes, and you'll need to convert those 2 data bytes into a single 14-bit number using the formulas that we've seen. Then I suggest that you write a new function which we can call pitch wheel. The pitch wheel function should take the 14-bit number, convert it first to a value in semitones, and then convert that into a frequency ratio. Store the frequency ratio inside of a new global variable that you declare, which I suggest you call G pitch bend ratio. Then, inside of the render function, multiply the note frequency by G pitch bend ratio before you set the pitch of the oscillator. This should give you an oscillator whose frequency goes up and down with the pitch wheel messages. Pause the video and try it. Here we have our MIDI synth, which we have extended to respond to pitch wheel messages. All of what we needed to do is inside of render.cpp. We talked more about the architecture of this synth and the classes involved in it in Lecture 15. We've added a few things to implement the pitch wheel. First of all, at the top of the file, we've added a global variable called G pitch bend ratio. As we saw in the slides, the purpose of this is to hold the ratio in frequency between where the note would normally sound with no pitch bend and where it should sound with our pitch wheel moved. The rest of these objects are more or less as they were before. Now I want to highlight one thing about the MIDI callback API, which is that we've declared a function prototype of our MIDI callback function here at the top of the file. The function that we're going to call when a MIDI message comes in is called MIDI event. Now, the reason that we have to declare it here with just a semicolon rather than its full implementation is that inside of setup, we are referring to MIDI event right here. If we hadn't previously declared a function prototype, we might get an error from the compiler that it didn't know that there was a function called MIDI event. The reason we've done this is that I've chosen to actually implement the MIDI event function down near the bottom of the file. Here we are. And the reason that I've done that is that this allows the MIDI event function to easily call the other functions we've declared like note on, note off, pitch wheel, etc. Generally speaking, the rule is whenever you have a function that needs to call a function that is declared lower down in the file than where it's declared, then you're going to need a function prototype at the top of the file. It can also be good practice just to always have function prototypes for every function that you write. In any case, here's our MIDI callback function, and we do a few things when a MIDI message comes in. First of all, we can display where the message came from and what its contents are. You can comment these out if you don't want to see this. Then we're going to go through and we're going to check the different types of messages. In the last lecture, we looked at note on messages and note off messages, and we won't look at that further here. What I've added is checking for pitch wheel messages, type KMM pitch bend. When we find a message of this type, then we get the 2 data bytes from it, and we can pass it to the function called pitch wheel. I've chosen to pass 2 7-bit arguments here. You could also, as I suggested, calculate the 14-bit value here and pass that to the pitch wheel function. Now let's have a look at the pitch wheel function itself. It's declared here above the MIDI event function. It takes in the 2 data bytes, and the first thing it does is convert those to a 14-bit value using the formula that we saw on the slides. That's an integer between 0 and 2 to the 14th minus 1, and we then need to rescale that to be between -2 and 2. Now here I've straightforwardly implemented the formula as a mathematical expression. You could equivalently use the map function to do this, where you would map wheel value from the range 0 to 16383 to the range -2.0 to 2.0. Note that map always works with floats, so you don't have to worry about losing the decimal points when you call it. Once I've got the bend measured in semitones, then I can convert it to a frequency ratio using the formula 2 to the n over 12, as we saw before. I'm storing that in this global variable called g pitch bend ratio. We're going to use this inside the render function. In the render function itself, we have a bunch of code at the top, which is responsible for getting the GUI sliders to set various parameters of the envelopes and the filter. This was covered in lecture 15, and I'm not going to recover it here. Then we have our for loop that goes through the number of audio frames as usual. Inside of here, before we set the frequency of the oscillator, we first need to multiply G center frequency, which is the frequency of the note, by G pitch bend ratio, which we just calculated. We can then set the frequency of the oscillator and handle all the rest as we did before. So remember on the slides I said that we need to save the note messages and the pitch wheel messages separately if we want to be able to remember them. That's effectively what we've done here. We're saving what happens with the note messages by calculating G center frequency, and we're saving what happens with the pitch wheel by calculating G pitch bend ratio. Then, once we're in render, it doesn't matter which message has come in most recently. We can always multiply the effect of both of them to get the final frequency of our oscillator. With that, we can run this and see how it works. Let's start very simple by just pressing a single key. We can use the pitch wheel. So you can see that the range is 2 semitones as we would expect. Now one thing to check is that if I change the note and then I release the pitch wheel, the value of the pitch wheel has persisted across MIDI note on messages. So there we have it, support for the MIDI pitch wheel. Next up, let's have a look at the MIDI control change message. As we saw last time, this contained a channel number, a controller number, and a controller value, where there are 16 channels and 128 possible controllers with 7-bit resolution or 128 possible values. MIDI control change messages affect every active note on the channel. Each controller number has its own unique meaning. Some of these might be specific to a particular synth, others are relatively standardized across the industry. One that's very standardized is control change 1, which is the modulation wheel. We'll see more on that in a minute. In the meantime, let's work out what we need to do to handle any control change message. The most important thing to remember is that these messages, like all MIDI messages, are persistent. When we receive the message, we're going to need to record its effect somewhere because we're probably going to need to use that later. The other thing that we need to do with a control change message is to rescale its range. Every MIDI control change has a range of 0 to 127, but in practice, most synthesis processes we're interested in might have their own ranges, so we'll need to rescale that range. The first thing we'll do with a MIDI controller is to implement detuned oscillators. We saw this all the way back in lecture 4, where it's common to produce a richer sound by mixing together two oscillators that have a similar but not identical frequency. The detuning results in beat frequencies according to the mathematical relationship indicated here. When we did this before, we had two different controls to adjust the oscillator frequencies. One of them adjusted the center frequency of both oscillators, and the other adjusted the detuning amount between them. We're going to do the same thing here, but using MIDI messages. The MIDI note messages will control the center frequency of the oscillators as they have been doing so far. The detuning ratio is going to be controlled by a MIDI control change message. We need to know something about the range of values we want for detuning. In this case, if we're using the formulas that we see at the bottom of the screen, we have a value of R that should range between 0 for no detuning and a relatively small amount, significantly less than 1. Your task then is to take the MIDI pitch wheel project you just worked with and change it from one oscillator to two. You'll need to change the G oscillator wavetable object to be a 2-element array. I suggest that you rename it to G oscillators, plural, so that everywhere it comes up in your project you'll immediately get an error message if you forget to change it. You'll need to initialize both of these objects in the setup function, though you only need to calculate the wavetable once. Then declare another global variable, call it G tuning. Make it of type float. This is going to hold the amount of detuning between the oscillators. A reasonable default value might be something like 0.002 or 0.2% to get just a slight detuning effect. Inside the render function, you'll need to set the frequency of both of these oscillators using the formulas we saw on the previous slide. You'll calculate the outputs of both oscillators, you'll mix them together, and then you'll apply the filter to the result. Once you've done that, you'll be able to hear the detuned oscillators in your synth, but the next step will be to control the detuning amount using a MIDI control change message. Here, the first thing to do is decide which MIDI controller number you're going to use to adjust the detuning. The easiest way to do this is just to run the project, turn one of the controls on your MIDI keyboard, and check the number that prints in the console. Then inside of your code, inside the function called MIDI event, you're going to have to look for messages of type KMM control change. I suggest that you declare a new function called control change, and when you get messages of type KMM control change, you call it with the controller number and the controller value. You'll then need to check whether the controller number matches the control that you just decided to use. If the controller number matches what you want to use for detuning, then rescale the controller value from a range of 0 to 127 to a range of, let's say, 0 to 0.01, and store that inside the variable g detuning. Once you've done this, you should find that you can change the detuning ratio between the oscillators by turning the controller on your keyboard. Pause the video here. And here we have the result. I'm going to start by talking about how we implement the detuning itself, and then we'll look at how we control it with MIDI. Down here, we've changed our oscillator from being a single wavetable object to being an array of 2 wavetable objects, and I've renamed it as G oscillators, plural. Inside of setup, I'm initializing both of those oscillators. You can see that here. I'm initializing array element 0 and array element 1. In principle, if I had an arbitrary number of oscillators, I could write a for loop to initialize all of them. Both the oscillators have the same wavetable. Back again to the top of the file, I've also declared a value called G detuning. This is the detuning ratio we talked about, and it defaults to a value of 0.002. We're going to use this value inside of our render function, so let's go down there next. Inside of our for loop, we're first going to calculate the note frequency and the pitch bend ratio as we did before to get the center frequency between the 2 oscillators. I'm then going to call set frequency twice, once for each oscillator. In the first case, I'm going to set the oscillator to the frequency times 1 minus the G tuning, and in the second case, I'll set the oscillator to the frequency times 1 plus the G tuning. This causes the frequency of the 2 oscillators to be slightly apart from one another. Then when it comes time to calculate the output of the oscillators, we have to gather the value from both of them, calling their process methods. Mixing their outputs is just adding the values, and then we multiply it by the amplitude which was generated from our ADSR envelope. Finally, we can filter that value and write it to the audio output as we did before. The next question is how to control the detuning ratio using MIDI control change messages. Back again to the top of the file. You'll see here that I have declared at the top a constant for which MIDI controller I want to use to control the detuning. I've used an enum statement for this to make it easy to declare additional controllers later on, and by doing it at the top of the file here, it becomes very easy to change the behavior of my program without having to go digging for magic numbers about which controllers I'm supposed to be responding to. Then we need to look at how we're handling the MIDI messages. We'll go down toward the bottom of the file, and you can see inside of the function called MIDI event, we are going through the different types of MIDI messages as we saw before, note on, note off, we saw pitch wheel messages. I've added one further type of message for KMM control change. When we get a control change message, I'm going to get the controller number and also the value, and then I'm going to call this function called control change. Notice, by the way, that I'm completely ignoring the MIDI channel information in this synth because I assume this is a very simple synth and it doesn't need to respond to channels differently. Now let's go find the control change function. So we'll scroll up here, and here it is. This function takes in 2 arguments, as we saw, the controller number and the value, and then I need to have an if statement to find out if the controller is one that I'm interested in. In this case, there's only one controller we care about, which is KMIDI controller detune, which I previously declared. If that's the controller that we have, then we can call the map function to map the controller value from the range 0 to 127 to the range 0 to 0.01, and we store that inside of G detuning as we did before. And I've just put a print message here to indicate that the value is changed. This could be just for debugging, and of course you could turn this off once it's working. We can run this project and see how it works. Now, the controller I'm going to use to change the detuning ratio is this one. So we can see that as we change this, notice that we see the messages indicating that the detuning ratio goes from 0 to 0.01. So we'll set it somewhere in the middle. And now we can play a note. And we can adjust the detuning ratio. And there we go, we can adjust the parameters of our synth using control change messages. Next up, let's look at a special case of the MIDI control change, which is the modulation wheel. Virtually any MIDI keyboard that has a pitch wheel will also have a mod wheel. Both of these were introduced in the MIDI Moog back in 1970, well before the MIDI protocol was ever introduced. The difference between the response of the pitch wheel and the mod wheel is that typically the pitch wheel is spring-loaded and will snap back to its center value, while the modulation wheel tends to stay in place wherever you've left it. You can use the modulation wheel for a whole variety of different types of modulation. This could, for example, be to change the cutoff frequency of a filter. You might use it to change some parameters of the oscillators, but most commonly you'll see the mod wheel used to add a vibrato effect to your sound. The way that we implement vibrato is with a low-frequency oscillator, whose output is in turn going to affect the frequency of our main oscillator. Changing the amplitude of that low-frequency oscillator will change the vibrato depth. Let's talk about this a little more. We've seen oscillators several times by now, and we've seen them used as audio sources. But oscillators can also be used as control signals. Typically speaking, an oscillator that we use as a control signal is going to change value much more slowly than an audio waveform. This is what's known as the low-frequency oscillator, or LFO. Vibrato is a very good example of this. It's a periodic change in the frequency of a sound. Vibrato will typically unfold at the range that the human hand might move back and forth, for example 3 to 6 hertz. The amount of frequency variation depends on the vibrato depth, and it could be anything from very small, just a fraction of a percent, maybe up to around half a semitone or so, 3% in either direction. The diagrams here show us how we implement the vibrato using an LFO. We're going to take two controls as inputs. There's going to be a vibrato rate, R, which is going to control the frequency of the LFO, and there's going to be a vibrato depth, D, which controls its amplitude. The LFO is going to generate a sine wave in this case. The output of that sine wave by default will start from a range of -1 to 1. We then multiply it by the vibrato depth to get the final output. We then have to multiply that again by the audio oscillator frequency and then finally add it to the audio frequency. This is going to give us the frequency of the audio oscillator, which is going to go up and down periodically as we see in the plot in the lower right-hand corner. That's just a very brief description of something that could be talked about in considerably more depth, but the purpose of this lecture is to focus on the MIDI controls. So let's go to the task from here. In the MIDI pitch wheel project, add an additional wavetable object to implement an LFO. You might call this G vibrato LFO, for example. Now this wavetable should implement a simple sine wave, which is going to be different than the waveforms of our audio oscillators. So inside of setup, you're going to have to figure out how to calculate a wavetable which holds only one single sine wave. See if you can adapt the code inside of setup to do that. Once you've set up the oscillator, then you can set its default frequency to something relatively low, let's say 5 hertz, and use the output of the vibrato LFO to modulate the frequency of the audio oscillators according to the diagram that we have here at the top of the screen. You can just start with some default values for vibrato frequency and vibrato depth, but once you've got that working, then make the vibrato depth controllable using the mod wheel. Remember that the mod wheel is just another MIDI control change message, it just happens to have the controller number of 1. So when you receive a control change message with a controller value of 1, you need to rescale the value of that message from its initial range of 0 to 127 to a range for the vibrato depth. For example, I recommend trying a range between 0 and 0.05. If you like, you can also add a second MIDI controller on your keyboard, which could adjust the vibrato speed. A sensible range for that might be something like 1 to 10 hertz. Once you've implemented this, in addition to the pitch wheel and the detuning, you should find that turning the mod wheel up produces a vibrato effect on your sound. Pause the video and try it. Here's the next step. As before, we'll first look at how the vibrato is implemented, and then we'll look at the MIDI controls for adjusting it. We've added, in addition to our two wavetable oscillators that generate the audio output, a third wavetable object which generates the vibrato LFO. I've also declared a global variable to control the vibrato depth. Notice I haven't had to declare a separate value for the vibrato frequency because that is a property of the wavetable object. Inside of setup, we have to initialize the vibrato LFO, so let's see how that's done. Here I've written a for loop which calculates a single oscillation of a sine wave over the range of 0 to the wavetable size. This is basically just adapting the code that we had here, but simplifying it to be only a single sine wave. I have called the setup method of G vibrato LFO to pass in that wavetable and of course to tell it the audio sample rate. So this is again just adapted from the code above. Now if we go down to the render function, we can see how this is used. Inside of the for loop, we are calculating our center frequency of the oscillators as we saw before. But before we do the detuning calculation, we have one more step to implement, and that is to adjust the frequency of the oscillators according to the output of the LFO. So this is implementing the block diagram we saw on the slides, and let's see why. The first thing that we do is we call gvibrato LFO.process. That generates the next sample of the low frequency oscillator. Remember that that's going to have a range between -1 and 1. We needed to rescale that by the vibrato depth. That might have a range between 0 for no vibrato and say 0.05 for a vibrato nearly a semitone in width. Once we have that, we add a value of 1.0 and then multiply the frequency. So in other words, the frequency is going to be equal to itself plus a factor that has to do with the vibrato LFO and its depth. Then the rest of the code works more or less the same way. Let's now look at how this is controlled. Back to the top of the file. I've declared a couple MIDI controller constants here. One is the mod wheel, which of course has a control value of 1, and then I have found this controller with a value of 75 just based on the default values that my keyboard sends out. You'll probably have different values here for your keyboard. The rest of the work is done inside of the control change function that we previously declared. That's down here at the bottom. We have the detune control, which we had before, that hasn't changed, but we're also checking for mod wheel messages. So if the controller number matches the value of 1, which is K MIDI controller mod wheel, then we're going to rescale its value from its normal range of 0 to 127 to the range of vibrato depth that we're interested in. You could potentially declare these control ranges as constants at the top of the file as well if you want. I've also added a controller for adjusting the vibrato rate. When that comes in, then we rescale the value to set the LFO frequency, which we call right here, gvibrato LFO.setFrequency with the value that I have just rescaled. I've also printed a message for whenever the LFO frequency changes. We can run this and see how it sounds. So notice that the mod wheel is currently at its minimum value, so if I play, we shouldn't hear any vibrato right now. And we have our controls here for adjusting the detuning ratio, which we had before, and also adjusting the vibrato frequency. So if I play a note now and manipulate the mod wheel, we should hear the vibrato start. Now I'll turn the detuning down a little bit so it's easier to tell what is the effect of the vibrato and what's the effect of the detuning. And now we can see that as we play notes, I can also change the speed on the fly while leaving the mod wheel in its upward position. So this is getting to be a reasonably complete synth. It responds to multiple key presses and keeps track of which ones came first. It has ADSR envelopes for the amplitude and the filter cutoff. It has two oscillators whose relative tuning can be adjusted, and it also implements vibrato with an LFO whose parameters can be adjusted with the mod wheel and with another MIDI controller. There's one more thing I want to add to it before we get to the end of this lecture. And here's the last thing. It's called Portamento. This is an effect where the pitch glides gradually from one note to the next rather than moving abruptly. On a synth without Portamento, the frequency over time might look like this, where it changes every time a new note comes in. With Portamento, we'll get a value that instead looks more like this, where receiving a new note causes the pitch to start moving toward its new value, but it might take a little bit of time to get there. This is a reasonably common effect on analog synths, and one way that it can be implemented fairly simply is by putting a low-pass filter on the pitch control voltage. That means that whenever the pitch control voltage wants to change abruptly, it instead has to move gradually and asymptotically toward its new value. The lower the cutoff frequency of this low-pass filter, the slower the pitch CV is going to move and the more pronounced the Portamento effect is going to be. An equivalent way to implement this in our code is going to be use an exponential segment generator to change the frequency every time we get a new MIDI note number. We saw the exponential segment generator in lecture 14 when we were using it as part of the ADSR envelope. If you look at the MIDI pitch wheel code, you'll find that in fact this class has already been included in there for you to use. To implement the Portamento, we need to declare an exponential segment object inside of our render.cpp. There's two ways that we could potentially do this. One is that the exponential segment could control the current center frequency of the note in hertz. Notice that this doesn't include the effect of the pitch wheel or the LFO for vibrato. The other way we could do this is that the exponential segment could control the MIDI note number, which would then be converted to a frequency every time we wanted to use it inside of render. For relatively small musical intervals, these will sound pretty similar. For larger intervals, you might get a marginally smoother effect by controlling the note number directly. The example that I'll show you just uses exponential segment to control the current center frequency because it slots in more easily to the structure we've already created. Your task then is to replace the current float called G center frequency with the exponential segment object. Whenever you want to change the note, instead of just changing G center frequency, you're going to call the ramp2 method of the exponential segment class. For more details on that, go back to lecture 14. Finally, use a new MIDI control change message to adjust the Portamento time. At its smallest value, you should hear no Portamento at all, and at its largest value, the Portamento should be fairly slow. A reasonable range of values here might go up to 0.5 or 1, let's say. This is the last task for this lecture, so pause the video and see if you can make it work. All right, we have now reached the final form of this project by adding a Portamento. We're again going to start by going through the Portamento itself and then talk about how we control it with MIDI. Actually, before we do that, I want to fess up to making a little bit of a bug in the previous example, and I'm going to show you where it happened. If we go down into the setup method, I did not initialize the frequency of the vibrato LFO. That meant that it defaulted to a frequency of 0. The way this manifested, and you might have encountered this in your own code, is that if you didn't change the controller for the vibrato frequency, you wouldn't actually hear any vibrato with the mod wheel initially. Back to the top. To implement the Portamento, we are going to need to declare a couple variables. We'll need to replace the previous float for G center frequency with an object of type exponential segment. Again, the file for this is already given to you in this project, but this is the first time that we are using it. We're also going to declare a float for the Portamento time. This is going to keep track of the value that we're going to set with our MIDI controller, which indicates how long the segments should be. Implementing the Portamento is mainly handled within the note on and note off function, so let's have a look at that there. Inside of note on, where previously we would have just set G center frequency to the value that we calculated here, now we're instead going to need to call the method called ramp2. What that means is that the frequency is going to gradually and exponentially approach this particular value over the amount of time given here. The same thing happens inside of note off, where previously, when an active note changed, we would have just set the center frequency to something different. We again have to call ramp2 to set it to a different value gradually. There are some changes in render to handle this as well, where before we just calculated our frequency by multiplying G center frequency times the pitch bend ratio. Here we have to call the process method of the exponential segment object. That's going to give us the current value of the center frequency, wherever it might be in the exponential segment. Then the rest of this is going to work the same as it did before. From there, we can see what needs to happen to control the Portamento using a MIDI controller. I've added one more MIDI control change message, which is Hey MIDI controller Portamento time. Its value is declared at the top of the file, and again, its controller number matches what my keyboard sends out by default. If the controller number matches this, then we are going to map the value from its range 0 to 127 to a range of 0 to 1 second, and that will be stored inside of this global variable called G Portamento time. Remember that G Portamento time is what is used inside of note on and note off for this ramp to method. So we can see here again the way that persistent state is really important in handling MIDI messages. When we get the control change message, we are not directly causing any ramps to take place, we're just storing its value for use later on. The only thing I skipped over here was the initialization of the exponential segment object, which also has to happen inside of setup. So let's just have a look at that. Here we have to call the method setSampleRate of G center frequency, just so that the object knows what the expected audio sample rate will be. And that's it. We can now run this and see how it sounds. And let's just start simple here. There's no Portamento by default. But we can adjust it with this particular controller. So you can see here the messages are saying that the Portamento time is being changed. And so now, we can try different values. So you can see when the Portamento time gets very long, it can become slightly strange. Maybe we just put just a little bit of Portamento on there. And of course, we still have all of the other effects that we previously had before. So there we go. That is our complete MIDI synth. And that brings us to the end of this lecture. We've just covered a two-part series on the MIDI protocol, covering most but not all of the most salient messages. Hopefully, on this basis, you could extend your code to handle other types of MIDI messages, such as channel pressure or program change. Remember that you can find more details on the MIDI specification in the companion materials for this lecture and the last one. We'll move on to a new topic next time, so don't forget to subscribe to be notified of the latest videos. And as always, you can keep in touch with us on social media or drop by any of our websites, our forum, our blog, or our knowledge base. Thanks very much for joining us for this lecture, and we'll see you for the next one.